Now, after we discuss the equilibrium model, let's move on to type of model called no arbitrage model. Now, we have seen that the equilibrium model on short rates work relatively well, and it's theoretically sound. It provides the closed-form solutions in a number of situations. So it's pretty good. But the equilibrium models actually have some fatal issues, and therefore it started to not be in the favor of the market because of those fatal issues. Now, in particular, you will find that if you adopt a equilibrium model, it will generate a sequence of a whole set of zero coupon bonds based on a particular realized interest rate short rate right now. Now, however, it doesn't really match what you actually observed in the market, because if you have a particular instantaneous interest rate, you can say use the overnight interest rate as a proxy for that. Under the equilibrium model, for a particular realized instantaneous short rate, there's only one shape possible, and that means that all the zero coupon bond prices are determined in a particular way. They're all linked in a particular functional form. But the market isn't really like that. For a particular realized instantaneous rate, there could be different sets of zero coupon bonds that are all valid. Let's say for a particular realized instantaneous short rate, then it means that in the market, the term structure curve can be drawn in different ways. There's more than one possible curve. So whereas in the equilibrium model, there's only one possible curve you can draw for a realized instantaneous rate. So since you can't really match the actual market condition, people will say, well, if your short rate model can't even match the term structure of interest rate that is materialized right now, how do I think under this process you will be able to price options well, right? So that casts some sort of doubts on that. Then people will then work, they'll people actively research to resolve that issue. So one of the ways to resolve that is, okay, let's try to have a set of models or a processes on instantaneous short rate that guarantees matches the current market condition. Okay, so how does this done? So essentially, in those processes, the drift of the process is really a function of time. We have seen the drift as a function of time for zero coupon bonds, but here what we're talking about here is the interest rate, the short rate model itself has the drift, where that drift is actually a function of time. So we will see what that really means. The first non-arbitrage model we're gonna talk about here is what we call the Hou-Lee model. This model here, you will see that as a function of t at the drift term here. Recall that for vessel check, you have a times b minus r bracket dt. and A, B are all parameters. So which means that the whole drift turn is not a function of time, has nothing to do with time. Here, this drift is a function of time of a form that we have to determine. So we don't know right now what that form is. This theta function is determined by matching the initial term structure of interest rate that we observe right now. Okay, this part is the same as the Vassilchak one. Initially, they actually built this as a, it's not like a model here. They built it in as, in their paper, it's a binomial tree model, but essentially that binomial tree model is basically a model we can specialize like this. Okay. Under the Hawley model, this theta is determined this way, where this f is really the time zero instantaneous forward rate at time t, really t between t and plus delta t, where delta t is approaching to zero. So this f subscript t is the partial derivative of f with regard to t. So df dt is this ft here. So this theta function is the partial derivative of the instantaneous forward rate and plus this part that relates to the volatility of the process. So under the Hawley model, the expected change of R, so basically it is roughly the slope of the forward curve. So if you get a forward curve, you roughly have that. So although you have this time function there as the drift, so that allows you to match the initial term structure of interest rate, because that this part basically is from the initial observed term structure of interest rate, and from here you determine this theta function here. So by definition, you matched your process. Your process will match exactly the initial term structure of interest rate. So just with that, the Hawley model still have the same form as the Vassilchak or CIR, and they have a bit more complicated form for options pricing, but then they still have closed form solutions. So it's just a little bit more complicated than Vassilchak here, but they have relatively similar form, and because they're all closed form solutions, so it's actually very nice for them to be used. Now, because of this, you can then use the Hawley model in a very similar ways as you use the Vassilchak model. So here, basically with this model here, you by design match the initial term structure of interest rate, and you have a whole bunch of closed form solutions that you can utilize to price options on zero coupon bonds, and you have a single factor model. You can then expand that to options on coupon bonds or swaptions. So this it's actually fairly nice, and it's it can show that as an improvement over the Vassilchak model. However, the by design, you have a time function there for the drift term. So you really don't have an explicit mean reversion. So you lose this mean reversion ability in the whole Lie model. And also that the whole Lie model also potentially give you negative risk-free instantaneous rates, which is the same problem that VasoCheck will also have as well. Only the CIR one would not have that, and the earlier log normal process would not have negative interest rate. But both whole Lie model and VasoCheck will have the possibility of instantaneous flow rate being negative.